The Chenab Bridge has been hit by an earthquake with a magnitude of 8.0 on the Richter scale. Passengers might think that this would soon happen. What actually happens is different. The rail deck remains unaffected by the earthquake. Can you explain how this is possible? The answer lies in the spherical bearings. The lower part of each bearing moves with the ground, but this motion does not transfer to the upper part. To isolate the rail deck, the Chenab Bridge also makes use of expansion joints. The way expansion joints work is a feast for the eyes. The movement of the box-shaped rubber structure makes this functioning possible. To understand why this bridge is safe, even in seismic zone 5 area, let's take a cross-section of its foundation. You can see a lot of interesting stuff here. This was the shape of the mountain before the construction work started here. An irregular sloped mountain. The minimum slope of this mountain was 43 degrees, and the maximum was 77 degrees. The first job of engineers is to cut these mountains so that the shape is suitable for construction. The rocks in these mountains are not so strong. It's a material called dolomite. Not suitable for erecting a strong foundation. Excavators were used in the initial stage of shape correction. After that, they employed a technique called pre-splitting. In pre-splitting, a lot of tiny explosives are kept in a close distance. Connect them together and they explode. Normal explosives break unnecessary portions of a rock. Using pre-splitting, you'll have greater control over the rock to be broken. The mountains look more clean now, but how to make them stable? The engineers used 3 methods to stabilize the slope: grouting, the use of anchor block, and shotcrete. The Himalayas are young mountains. The rocks in this region have a lot of minor cracks inside them. In the grouting technique, we inject cement into these voids. The cement acts as a glue and the rock becomes stronger. You might have seen a lot of strange-looking blocks in construction photographs of Chenab Bridge. This is a smart slope stabilization technique called anchor block stabilization. In this method, the workers make holes on the slope. After that, they insert a special rod with a lot of tendons in it. In this project, they used divvy-dag tie rods. Now it's time for grouting. Once the grout is hardened, a block is kept on the rod. Now comes the use of a powerful hydraulic jack. The hydraulic jack pulls and keeps the steel tendon in extreme tension. After that, using a wedge arrangement, the steel tendon is kept in tension, even if the hydraulic jack is removed. Now, can you predict the force produced by the concrete block? The steel tendon in tension wants to reduce its length, but the block is not allowing that. This means the concrete block will press the slope inward. This compressive force will greatly increase the stability of the slope. Their next technique is shotcrete. Using this special machine, concrete is sprayed on the mountain rocks. This technique increases the stability of the mountain further. Now, the mountain is ready to support the heavy steel material. Next, they prepare the concrete foundation so that the steel piers of the bridge can be erected on it. Erection of the steel piers is done in a rather straightforward way. But how to erect the arch? No crane in the world will be able to do this task. That's why the engineers first erected the longest cable crane tower in the world, with a span of 915 meters. This cable crane is capable of lifting up to 35 tons. All the structural elements needed for the bridge were transported via these cables. Each arch segment is made up of box sections of 10 to 12 meters length. The different elements of the arch were connected together mainly using nuts and bolts. More than 600,000 of nuts and bolts were required for this work. The arch construction is progressing in a step-by-step manner. During all these processes, you can see cable stays supporting both halves of arches from the steel pier. Without these cables, you can guess what will happen to the arches. They'll fall down due to their own weight. More interestingly, to balance the force on the first main pier, the cable stays were connected to the neighboring pier in the opposite direction. Without these stay cables, the main piers would bend inward. Now comes the crucial day, the completion of the arch erection. Both halves of the arches met on this day. This process is known as arch closure. The main issue in arch closure is that even minor alignment issues can cause the final connection an impossible task for the workers. Even if the alignment is perfect, the heavy wind will make the assembly work difficult. So the first task before the structural element installation is to align both the halves perfectly. And also, we need a temporary connection between them. This is why this special hydraulic jack is used. By adjusting the green member of the jack, the horizontal distance between the arches can be adjusted. You can see currently only 6 members are missing from the arch. The yellow portion helps in adjusting the vertical distance. The bottom cord can be fitted. Once this is done, the force in the green member of jack can be released now, and a few more elements can be installed. Now they introduce the next jack. Until the perfect gap is achieved in the top cord, adjust this jack. Now, the top cord, the final structural element of the Chenab Bridge, is installed. This was a big celebration. Both arch halves got connected perfectly. The jacks have done their job. Once the arches are connected together, the support cables are no longer needed. The half arches support each other. They erected piers even above the arches. For the erection of the arch, the workers worked meticulously. Even their food was delivered by crane on the arch. The next stage of construction is the installation of decks. The rail track will be laid on this deck. We've already studied about the expansion joints of Chenab Bridge. The main span of Chenab Bridge uses 2 such expansion joints. The bridge is separated into 3 pieces with the help of these expansion joints. In short, the rail deck of the Chenab Bridge is not fixed to any structure from the ground. It's just floating on all these bearings. All this sophisticated engineering, planning, and execution are the reason why the Chenab Bridge became the tallest rail bridge in the world. Its height is 359 meters above the Chenab River, 35 meters taller than the Eiffel Tower. You might have wondered why Chenab Bridge uses the arch bridge technology. Why not a simple pillar bridge? Look at the height of the pillars needed in this case. This would also obstruct the river flow below. The arch shape in an arch bridge is always a parabola. Why not any other shape? To get the answer for this, let's do an experiment.
Parabolic versus a circular arch. When I keep a weight on the circular arch, now let's keep the same weight on the parabolic arch. Wow, it is carrying the weight easily. Let's add one more weight. Perfect. It is even carrying an extra weight. So parabolic arch is obviously a super strong shape. Now it's time to prove logically why parabolic arch is the best self-supporting structure.
Let's tie a gigantic chain across the mountains of the Chenab. Thank you, King Kong, for your help. The shape this chain forms is a catenary. However, for simplification, we can approximate this shape as a parabola. Even if you try to hold it in some other shape, it won't stay there. A chain can support only a normal tension force. Now the tricky part. Let's solidify this parabolic chain. Now let's flip the direction of the gravitational force. Since the external force has flipped its direction, the internal stress will also flip its direction and become purely compressive. Now just flip this entire arrangement. Wow! It becomes an exact arch bridge. The compressive force developed by this parabolic structure is exactly at the middle of the section. Such structures aren't always stable. You can see why a structure may not be stable when the forces do not have this quality. This is why the parabolic arch is the best self-supporting structure. Now let's construct a road deck below this arch. This arch bridge is unnecessarily huge. There's one more way to achieve the same objective. Just shift the supporting arch down. Here again, the force induced in the arch is the same. If you were the chief engineer in charge of this project, which design would you choose? Obviously, the above-deck design, right? The reason is simple. You will save a ton on construction materials. The Chenab Bridge uses a ballastless track. Almost all high-speed railway projects use this technology. These animations illustrate how the different components in the ballastless track absorb vibrations. This bridge is designed to support a train with a maximum speed of up to 100 kilometers per hour. Ballast tracks have the issue of dust pollution, and they have a low life expectancy. So far, we've seen 2 expansion joints of Chenab Bridge. It should be noted that the bridge has 1 more expansion joint, but slightly away from the arch section. In short, the 3 expansion joints separate the bridge into 4 pieces. The bridge is even designed for redundancy. This means even if one of its piers gets damaged, the bridge will still remain stable. The train will still be able to cross the bridge, but at a maximum speed of 30 kilometers per hour. Chenab Bridge is connecting the Kashmir Valley to the rest of India via rail link for the first time.
Huge mountains, weak rock, inaccessible terrain, heavy wind and earthquake-prone area. Chenab Bridge project overcame all these hurdles and became the tallest railways in the world. Hats off to the engineers behind this project for their brilliant design and meticulous execution. Before you leave this video, please subscribe to this channel, and if you truly want to support us, please check out our Patreon page and pledge your support. Take care, bye bye.